What is the connection between a steam engine and a collapsed star? Not much, you might think. There is, however, a very deep and subtle connection that is still not completely understood. James Prescott Joule, the son of a wealthy Manchester brewer, was taught physics by John Dalton, famous for introducing the idea of atoms into chemistry. When Joule inherited the brewery, he began experimenting with ways to make the brewing process more efficient. These investigations led to one of the most important principles in physics, the conservation of energy, also known as the first law of thermodynamics, which Joule established in the 1840s. Although energy may be converted from one form into another, if all types of energy are taken into account, including heat, then the total amount of energy never changes. We may burn coal to heat water and produce steam that drives a turbine to generate electricity that powers our computers. But at each step, the total amount of energy remains the same if we include the heat that is emitted. In the early years of the 19th century, the development of the steam engine was rapidly increasing Britain's military and industrial strength. Several decades before Joule's experiments, Sadie Carnot realised that if France was going to maintain her military position, she was going to have to develop more efficient steam engines. Sadie had trained as a military engineer and was the son of Lazare Carnot, who as Minister for War had established France's Revolutionary Army. Sadie Carnot is responsible for the second pillar of thermodynamics. Many processes conserve energy but are never seen. For instance, heat never flows from a cold object, such as a lump of ice, into a warm object, such as a cup of tea. If this were possible, we could imagine adding ice to the tea in such a way that the ice becomes colder and the tea gets warmer. This could conserve energy, yet we know that it never happens. We cannot boil a cup of tea by adding any amount of ice to it. Carnot invented the concept of entropy as a bookkeeping device to account for this prohibition. He defined entropy as a quantity of heat divided by the temperature. For a given amount of heat, the entropy is smaller at a high temperature than at a low temperature, so when heat is transferred from a hot object to a cold object, entropy increases, whereas if heat were transferred from a cold object to a hot object, entropy would decrease. We are very familiar with the first of these processes, but our tea time experiments tell us that the second process never happens. Carnot captured this observation in the statement that in any allowed process, the total entropy of the universe can never decrease. This is the second law of thermodynamics. It is now known to be due to the statistical behaviour of large numbers of interacting particles. The second law of thermodynamics is less familiar than the first, but it is equally important. One of its consequences is that when energy is converted from one form into another in a power station, some of the energy is always lost as heat. It is therefore impossible to convert all the energy in a lump of coal into electricity, as some of the energy will always escape as heat. However, another consequence of the second law is that by increasing the temperature difference between the turbines and the surrounding environment, the proportion of the energy that is lost as heat can be reduced, thereby improving the efficiency of the power station. So there are very important real-world applications to the second law, as well as some rather otherworldly applications that we will move on to now. Israeli physicist Jacob Bekenstein worried that black holes might offer the universe the ultimate garbage disposal system by which it could lose some of its entropy. Black holes are seemingly featureless and therefore have zero entropy, and any material falling into the black hole would be lost along with the entropy that it contains. This appeared to violate the second law of thermodynamics, which states that in any process the entropy of the universe can never decrease. After some contemplation, Bekenstein realised that there might be a solution. When matter falls into a black hole, the black hole's mass increases and it therefore increases in size. In particular, the surface area of the black hole's event horizon increases. Perhaps this increase in the surface area of the event horizon might compensate for the loss of entropy contained in the material falling into the black hole. Hawking had recently proved that in all physical processes, the total area of black hole event horizons can never decrease. As described in our previous video, Hawking crosses the event horizon. Bekenstein was struck by the parallel between Hawking's result and the second law of thermodynamics. Bekenstein tentatively proposed identifying the surface area of the event horizon of a black hole with the black hole's entropy. But how could this be? The area law of black holes is a geometrical result about gravity, whereas the second law of thermodynamics is a law about the statistical behaviour of heat. Hawking's reaction when he heard of Bekenstein's proposal was that it was ridiculous. It could not possibly be true. Hawking went to bed that night convinced there must be a counter-argument that would demolish Bekenstein's idea. But he could not sleep. Hawking knew that any object that had entropy must also have a temperature, and that any object with a temperature above absolute zero must emit radiation. The hotter the body, the more radiation is emitted. But black holes are supposed to be inherently black. Nothing can escape from a black hole, so how could they emit radiation? Then Hawking had a revelation. He realised there were flaws in his own argument and that Bekenstein was correct. The surface area of the event horizon of a black hole really is a measure of the black hole's entropy. And therefore, like any body with entropy, the black hole must have a well-defined temperature and must therefore emit radiation. Despite this counterintuitive conclusion, everything now fitted together perfectly. There was no chance that Hawking would get any sleep now. But his illness had progressed to the point where he could not rise and dress himself without the assistance of his nurse. He had to wait several hours for his nurse to arrive before he could get up and put his ideas down on paper. General relativity remains the best theory of gravity that we have. But general relativity is a classical theory, not a quantum theory, and this was the crux of Hawking's breakthrough. It is true that when a black hole is modelled using general relativity, its temperature is zero, because, as everyone knew, radiation may fall into a black hole but nothing ever comes out, so black holes do not give off heat. However, although general relativity is a fantastically accurate theory, the world plays by the rules of quantum mechanics, so any description of black holes in the real world must incorporate the effects of quantum mechanics. Hawking realised that when quantum effects are included, black holes have a non-zero temperature, and consequently black holes are not completely black, they emit radiation. Hawking announced his startling conclusion at a meeting of his colleagues in February 1974 and was met with utter disbelief. This was the first link between gravity and quantum mechanics that anyone had devised, so it is no surprise that it took physicists a while to realise that Hawking's bold idea must be true. It is very surprising that a temperature can be assigned to a black hole, and contrary to what everyone expected, the radiation emitted by a black hole is now known as Hawking radiation. If you fell into a black hole, you would be stretched and crushed and vaporised well before you reached the centre of the black hole. Despite the violence that might be going on within the black hole, the temperature referred to by Hawking is that would be observed by someone outside the black hole, and this can be incredibly low. According to Hawking's calculations, a black hole with a mass 10 times the mass of the Sun would have a temperature just a 10 millionth of a degree above absolute zero, and would therefore emit hardly any radiation at all. In fact, this radiation would be completely swamped by background radiation, so it would be totally undetectable, unfortunately. Hawking speculated that if the early universe was quite lumpy, then some of the denser regions might have undergone the ultimate gravitational collapse to form primordial mini black holes in the immediate aftermath of the Big Bang. These hypothetical mini black holes might have a mass equal to that of an asteroid packed into a region smaller than an atom. Their low mass would make them much hotter than stellar mass black holes, and being hot, they would emit large amounts of radiation, thereby losing some of their mass. This decrease in mass would raise their temperature further, and this would further increase the radiation they emit in a runaway process that can only end one way. The temperature of a mini black hole would rise dramatically in its final moments until it exploded and disappeared in a huge blast of radiation. If primordial black holes really exist, then it should be possible for astronomers to detect them going bang as they disappear in a puff of gamma rays. The smallest such primordial black holes would already have exploded. Black holes with a mountain-sized mass of around 100 billion kilograms should currently be on the verge of detonation. Slightly larger, and the mini black holes will continue emitting X-rays and gamma rays for many eons to come. But to date, none have ever been seen. Whether or not mini black holes actually exist, there is no doubt that the general principles of Hawking's theory are correct, and that black holes do emit Hawking radiation. The combination of general relativity, quantum mechanics and thermodynamics mesh together so well that they must have an important role in the fundamental structure of the universe. This remains the most important idea connecting quantum mechanics and gravity. It is one of the most profound ideas in the history of physics. Thank you for watching the video. I hope you enjoyed it and subscribe to the video channel, and please don't forget to click the like button. Some of the ideas discussed in the video are quite technical because this is the outer fringes of modern physics. If you'd like to read the article, it's available on my blog at the address on screen. So thank you again for watching the video.